Hello, I'm glad to be here. I think partly why I'm here is the KAVLI Prize, which will be awarded at the beginning of September. The topic of that prize is the work I did back in 1970, and that was on an area that I didn't really have much specialization in. It began with a talk by Ed Fraser, but what he was actually discussing had been discovered in 1960 by Bob Layton and his group that were working at Mount Wilson. My work was on the theory of convection, and I had some model envelopes which I was using. Bob Layton had invented a new way of imaging the velocities on the solar surface, and a few years later Ed Fraser had gone to Kitt Peak. He was also a graduate student at UC Berkeley in a slightly different department from mine, but he went to Kitt Peak and observed the sun using instruments that were available to him. He found that the oscillations which had been discovered by Bob Layton's group, in fact were disrupted by convection, whereas the ideas at the time had the basis that the sound waves that were on the solar surface were generated by convection. So I felt that Ed Fraser's work was kind of a paradigm shift in that. At the same time, John Bacall came through the department at UC Berkeley. He was working on what was called the solar neutrino problem, and he was not too happy that we didn't have a model of the sun generated at UC Berkeley. So I set about to calculate a model of the sun for him, which I sent down to him, and he promptly replied with a whole host of things that needed to be fixed. I was on my way out of the UC department at that time because I had finished my degree, but I found Ed Fraser's observations to be interesting, and also I found that the offer from John Bacall to work on the solar neutrino problem in Caltech was something that I wanted to accept. So I headed south and joined up with Bacall at Caltech. In the meantime, this little piece is part of the story, which is an object lesson in how you should manage things and be aware of everything that your instrument's trying to tell you. This is a picture of Bob Howard at the 150-foot tower spectrograph, which was being set up to be automated with the Babcock magnetograph. In this system, the red and blue wings are servoed so they balance, and that means that if the velocity on the surface where the slit is set is changing, this yardstick, which is attached to the servo lever, will go up and down. And Bob noticed that this servo was in fact going up and down with a 5-minute period before Bob Layton announced his results. Bob Howard didn't actually say anything about this. He didn't pay much attention. So that was one of those things that happen if you're too focused on what you're doing and not paying attention to all the details. This is a Doppler image obtained by Bob Layton, Robert Noyes, and George Simon in their discovery paper from the photographic subtraction technique that they invented. You can see around the image that there is quite a bit of up and down motion detected with the Doppler shift. The center is just 5-minute oscillations, and towards the limb, you see a pattern which we now know to be the supergranulation. This is a modern picture taken with MDI, Michelson Doppler imager system on the SOHO spacecraft, and it uses a filtergram technique to measure velocities, and it has a much higher spatial resolution and a better flat field, so all of the ripples in the previous slide don't show up. This is what Ed Fraser found in his analysis of the velocity measurements, because he used a two-dimensional array instead of a one-dimensional array, which had been done before. He was able to fully resolve what we now know to be the critical parameter describing the motions, namely the total horizontal wavelength or wave number. That's down at the bottom. It's what we call K, which is the term that goes into the Fourier transform, and the wavelength is then the inverse of the K, so the shortest wavelengths are on the right and the longest wavelengths are on the left. In a similar fashion, there's a measurement of the period, which we call omega, or this is the angular frequency, and the period is 2 pi over this omega, and so the 5-minute oscillations are right in this band here. And what Ed found was this material down at the bottom is the convection, and these are the oscillations up on the top. And this is what I had available to me at the time as information for what was going on the solar surface. What I wanted to do was to see how these waves can propagate in the solar envelope, and so I took a model of the solar envelope that I had, and I calculated their acoustic properties as a function of position from the chromosphere, or slightly above the chromosphere, down to wherever the waves turned around and became trapped. What I found was that there are some mode lines running diagonally on this K omega diagram, which is where the oscillations have to be found when you see them on the solar surface. So these are effectively tones like you would have in an organ pipe, with the fundamental, which has different behaviors, I now know, and the number of nodes plus 1 in the radial direction is given by the modal number here. So there's basically no nodes in the fundamental. What is happening in the interior is that the waves propagate around the circumference of the sun at an angle, and every time they hit the photosphere, they are hitting a layer which is forbidden, and so they're reflected back towards the interior. So they bounce around the surface in the manner shown here, and if they happen to come back and are in harmony with the ones from the other going the other direction, then they'll set up a resonant mode, which will be more or less at the frequency which allows this overlap to occur. The rays which are more oblique have a shorter horizontal wavelength or a higher horizontal wave number. And if you want to get a ray to go towards the center of the sun, it has to start out more or less vertically, and then it will bounce around. This is the modern observation, which have now been done with the systems on the Solar Dynamics Observatory. This is from the Michelson Doppler imager on this SOHO spacecraft. And the dashed lines, which you can see here, are what I calculated in 1970 as to where the modes should be. The fact that they're at the wrong frequency, the frequency I have here is too high, that indicates that I had the wrong adiabat for my convective envelope. It's too hot and too shallow. So that my adiabat should have been lower, and the waves then would have had a somewhat lower frequency because they would have been in a cooler part of the sun, part of the solar envelope. This is the verification of my predictions, which were done in 1975 by Franz Steubner. Initially, I had been assuming that there would be a rush to verify my prediction. I waited 2 years and there was nothing going on, so I persuaded graduate student Ed Rhodes to see if we couldn't find a way of verifying or testing my prediction of these diagonal lines. At the time, there weren't really any instruments available to do this work. I think perhaps what Ed Fraser had used at Kitt Peak might have worked, but we didn't try Kitt Peak. We went to Sac Peak instead, and George Simon was there, and he was helpful. And we set up a system which allowed us to do the two-dimensional observations and isolate the total horizontal wave number. If you observe only in one dimension, you get one component of the wave number, but you'll have no control over the other direction in the horizontal space. As Ed Rhodes was preparing the analysis, which was difficult to produce at the time, our computers weren't really set up for it, but in the meantime, Franz Steubner, who had been doing this type of work over in Europe, published a prediction or a verification of the predicted modes that we had calculated, and you can see that he was finding more or less the same offset that we had in our current comparison to the observations. The verification diagram was then used by us in a slightly later publication, where we were able to test the models, test the predicted locations of the resonant modes using two different models, one with a convective envelope of 8.7% and the other at 0.3% of the solar mass, a much shallower envelope, much hotter, which was closer to what I had done initially. The quantitative comparison was done on diagrams like this, where we basically took slices through the K omega diagram in a direction where we just isolated the frequency. So this is the frequency down here, and then we have the dependence of this frequency on the convective envelope mode mass, or as we were doing at the time, something called the L/H mixing length to pressure scale height parameter, which everyone used then and continues to use now in most calculations of the solar envelope structure. One of the things we were particularly excited about with the use of helioseismology was the opportunity it provides to measure the translational motion of the solar plasma underneath the viewing box that we're having to record the motions for. If the plasma is moving in the direction of rotation, then the waves are pulled in that direction, and the ups and downs will pass by more quickly, so the frequency will be higher. If the motion of the plasma is against the rotation, then the waves appear to be more stationary and the frequency is lower. So by comparing the frequencies of the waves traveling with the rotation against relative to the waves traveling against the rotation, you can determine the rotation rate of the solar plasma. Many different modes can be used, and they penetrate to different depths. So in fact, this provides a way of measuring the depth dependence of solar rotation. The figures on the right show how the observed ridges are both lower and higher. They're lower at the lower frequencies and higher at the positive frequencies. And if you add in the effect of the rotation in the analysis, as we do in the right-hand figures, then in fact the ridges are the same on both, relative to the theoretical ridges are the same on both. So this provides a way of getting the solar dynamics in addition to the structure. After the initial observations and analysis that were on the previous slides, we continued to work at UCLA on calculating new solar models. We added additional physics and did some complete solar models. This is a figure from a paper that was in a non-refereed volume by Hill and Jaboski. There's several nice papers in that volume. This is figure 3 out of that paper, and I've added some additional notation. The figure in the volume itself doesn't have much explanation. You have to read the text carefully to get this information out. So there are basically 3 models that we plotted on this at 2 different values of the mixing length to scale height, as indicated. The dashed line is the previous models, which had not included the improved physics. The equation of state in particular had a Coulomb term added. And then the red line, which I've put in, is an interpolation between these two at the value of L over H, which we concluded would be, which actually fit a full solar model. So this was a status of what we were doing. It wasn't necessarily the best in the world, but it was good. One of the things that distracted us at this time was the fact that I was busy working to get a space experiment established in NASA. I went to several meetings at NASA headquarters and met with Dave Bolin. This reference down at the bottom here is a nice summary that helped me remember some of the dates that were involved. There was a sequence of meetings. One was in Boulder, and we kind of met in a meeting room there. There were a fair number of us, but not everybody. And we decided at that meeting that we should organize a much broader meeting that would have a published outcome. And so I was nominated to organize that, and we got it together for the late summer of 1983. So things were moving, but not super fast. After that, things actually picked up speed. The meeting, which followed on was back in NASA headquarters again, and was dubbed the Trilateral meeting because the Japanese Space Agency was invited to join NASA and ESA. ESA had a pretty well advanced program of doing space experiments. They had an experiment called DISCO, which was a spinning spacecraft, and eventually it was decided in this joint planning group that we should have a triaxis stabilized mission, which became known as SOHO, and that was basically defined at this trilateral meeting and the follow-on joint planning group, which had its meeting subsequently over at STEC in Europe. Eventually we did get the SOHO spacecraft built, and the experiments which went on there included the one from DISCO, which became the GOLF, Global Oscillations at Low Frequencies experiment, and I participated in that very actively. One of the leaders of that group was Sylvain Turchez, and she wrote this paper, which was quite influential. I've abstracted some things from it, the principal results. I didn't put everybody's institutions on this because that would have taken a lot of space. The idea is that you can calculate the sound speed in the sun just from the frequencies of oscillations that you've observed. You don't have to have a solar model. The inverse theory produces the sound speed as its outcome. You can then calculate a standard solar model using various techniques, and this is an example of two which were done at Saclay, and the other was Model S that Christensen Dalsgaard was sort of the leader on. It was a joint project of a large number of people. And you can see that the model sound speed really tracks the inverse theory sound speed quite accurately. From the models that you've created matching the inverse theory, you can calculate the detection rates of various solar neutrino experiments. There's the gallium experiment, the chlorine experiment, and the scattering experiment using water. And the predicted rates are these, and you can see that the actual detections are quite a bit less than the predicted rates, over a factor of 2 in the case of the chlorine experiment, which was the classic one that was done initially. The scattering experiments in water also were about a factor of 2 below what was expected. After the beginning kind of was concluding, I continued to work on, and first thing that we wanted to do, Ed Rhodes and I participated in a variety of meetings to plan for the inclusion of a helioseismology instrument on a spacecraft, which turned out to be the SOHO spacecraft. So we helped define the ways that would happen. I collaborated with John Bacall in the calculation of solar neutrino fluxes, and this collaboration was pretty intense at times, but it was quite rewarding. I did other things besides just solar physics. In particular, I had the unconventional idea that the cause for what's known as the T Tauri phenomenon was a result of material falling into the T Tauri stars rather than being ejected. We now know that in fact both of these things are happening at the same time. But at the early stages there, I went to Mount Wilson's 100-inch telescope and the Palomar 200-inch telescope to obtain line profiles to help confirm whether this idea I had was correct or not. The rotating infall model is something that people are still using to study these young stars. And in 1985, kind of a life-changing thing for me was I accepted the responsibility for managing the program of solar observations at the Mount Wilson 150-foot tower telescope, which has as its primary output the distribution of magnetic fields and the study of the differential rotation at the solar surface. And I added the capability for observing 6 different line combinations as something that could allow us to study the altitude dependence of the rotation in the solar atmosphere. So that's pretty much what's occupied me for the remainder of my time that I do research, and I'm still working with that. So thank you. At Nick Argy's recommendation, I added this slide, which has a few thoughts that I want to leave with you, sort of a lessons learned slide. And first off is starting off to pay attention to what at the moment looks to be the most important thing that you can tackle. For me, that was the solar neutrino problem. It certainly was important, and eventually we did make a contribution to that. Another thing is don't always believe everything you're told. The conventional wisdom sometimes is wrong, maybe in little ways, maybe in bigger ways, but anyhow, you don't have to take it as gospel and look at places where it might need improvement. And then the lesson from the second slide of the series is to pay attention to what your instrument is trying to tell you. Sometimes it's saying something you're not expecting, and if you just ignore it, then you'll miss an opportunity possibly to discover something new. And then a lesson from one of my recent works on the global solar oscillations, where we're searching for the gravity modes. The result is okay to publish, but if it needs to be verified, that's okay. But you need to wait for the verification before you really believe it. And if the verification doesn't verify it, then well, don't continue to argue. Maybe look for errors in what was done to verify it, but if those don't show up, then well, your hypothesis or your tentative results just maybe weren't true. So those few things to think about that I've used in guiding my research over the years. So thank you.